a member
Recording
of
in progress.
this set, this color set. This statement here is a true statement because red is a member of this set. However, here in this example, blue is a member of this set. This statement is false because blue is not a member of this set. If we use this symbol here, you see, this symbol is read as is not a member of. If we change this statement to here, blue is not a member of this set, and this statement is true. Okay, so in this slide, we need to recognize, remember two symbols. One is here, is a member of. Here is not a member of. Equality of sets. Two sets are equal if they have the same members. Okay, remember, memorize that we said earlier. Sets are not ordered and there's no repeats in sets. So all we need to do is to check whether all of the elements in the first set are in the second or not, or vice versa. Okay, say for example here in this example, two elements in the first set, 1 and 2. Both are the elements in the second one. So these two sets are equal. Here we have more examples. This one is equal to here, although the order for green and yellow is different in the first set and second, but they are equal. How about this? Are this and the here equal? So what is your answer? Let's see. Yes, very good. So this one is equal, these two, okay? Because there's no repeats in the sets. So consider here just, it's exactly the same as this one. Okay, very good. Now remember, I said earlier, you have already seen that is a member of symbol in our last week's lecture. So here it is. Remember, this is about eigendecomposition. We said this capital case A is a member of, in the real value space, we have, what is this? N by N denotes a square matrix. So A is a member of the square matrix family. Here again, that is the symbol, is a member of, so eigenvalue is a member of, what is this within this today? That is real value set. Okay, so you have already seen this. Quite often, these symbols would be used in research paper, writing in mathematical way. Okay, so cardinality of a finite set. We talk about infinite set, and now we talk about a finite set. For a finite set, the cardinality is the number of elements in the set. Okay, it is denoted using the symbol like a hash sign here, or with a vertical bar like here. Okay, we have a set A, and then vertical bar surrounding this A, giving 3. That is because we have 3 elements in set A. Or you can write it as here, hash in front of the set equal to 3. That means, there are only 3 elements in this set. Don't be confused with norm. When you learn linear algebra, the norm of a vector. For that one, we have a double vertical bars on each side of a vector. Okay. A little bit more. Here, subsets. The set A is a subset of the set B if and only if either the set A is empty or every every element of A is also an element of B. So by this definition, empty set is a subset of any set. Okay, that is by definition. And now let's see the other one, proper subset. The first one is subset. The next one is proper subset. The set A is a proper subset of the set B if and only if A is a subset of B but not equal to B. So have a look at the symbols we used for subset and proper subset. The difference is that for proper subset, we don't have the underscore here anymore. Okay, so we have here for subset denotes these two sides may be equal, maybe not. But here for sure, two subsets cannot be equal. Similarly to is a member, is not a member, we can also have a line through these two symbols so that we can denote the opposite. For example, here, the side on the left-hand side of this symbol is not a proper subset of here. Okay, so have a look at it here. Understand the difference between subset and a proper subset. By definition, all empty set is a subset of any set. Okay, by definition here. A proper subset, A is a subset of B, but not equal to B. Exercise. I give you 1 minute. Use your pen and notebook, write down your answer for these questions, and then we discuss them together. Okay, how about the first one? Is the statement here true or false? Let me have a look at your answer. For whatever the reason, I cannot open it. Okay. Sorry, I just want to see the chart. For some reason, I cannot see them. But anyway, the first one should be true. I hope you have answered it correctly. Because here we have repeats, forget repeats, then we have 3, 10, and minus 1. So they are equal. What about the second one? I really want to know your answer. Let me try one more time. Okay, that's good. False. Excellent. Very good. So empty set here on the left-hand side is empty set. This one, we have one element that is 0. So they are not equal. Okay. Question 2 here, the answer should be false. False. The reason is that this on the left-hand side, that is empty side. There's no element in it. Okay. But here on the right-hand side, that is not an empty set. We have one single element in it that is 0. Now, the third one. Third one, true, lovely, excellent. Yeah. So the third one, remember I said by the definition, empty set is a subset of all sets. Okay. And of course, it is, here on the right-hand side, that is not an empty set. We have 3 elements in it. So that is why this one in this statement, this empty set is a proper subset of the right one, the right-hand side one, okay? Because they are not equal. Empty set is a subset of any set. So that's why this one is correct. Now, number 4. False. Lovely. That's right. Okay. Number 4 here. This one, the answer is false. However, if I change it, add a horizontal bar here, add a bar under this symbol, then it is true. Okay. At the moment, because on the right-hand side and the left-hand side, both are 1, 2, 3 elements. So they are equal. So we cannot use proper subset symbol here. Now, next one. Write down the value of each of the following. So what is this symbol? Symbol here means cardinality. What is your answer for number 1? 0. And then we also see 1, 0. 0 is correct, okay? Because we have no elements here, so it is 0. What about here? The second one. The second one. 1, 1, 1. I saw 0. 2, 1, 0. Okay. For the second one, the answer is 1. 1 is correct. 1 is correct. How do you do this? Okay, think about it, listen carefully. Now, imagine each empty set, the empty set, the outermost empty set here, see the curly bracket, the empty set is a box. Okay, in that box you have nothing, a bigger box. And now, when I put a smaller box inside of this bigger box, if I ask you, okay, how many elements in that bigger box? You would see 1, right? Similarly to here, that is why for second one here, the cardinality is equal to 1. Consider the outermost here, the outermost curly pair of curly brackets as a bigger empty box. Inside we have a smaller one. So if I ask you the cardinality, this one is equal to 1. I hope it is clear. Okay, now, okay, thank you. So next one, Venn diagrams. Venn diagrams. Venn diagrams are a way of describing sets on the how they are related to one another in pictures. So each set here, set A, set B, is represented as a circle with the values that the set contains written inside in the boundary. See, for example, for set A, we have elements 2, 3, 5, 6. For set B, we have 3, 4, 6, 7. But sets that share the same elements are represented as overlapping circles. That is this part, because both 3 and 6 appearing in both sides, A and B. Now you see here, universe. Each value that we work with in one of our specifications must be drawn from a universe. It tells us the limits on the values that a variable may take. So useful universes, at least some of them here. So natural numbers, integers, real numbers, and truth values like true or false. In addition, we sometimes use alphabets as universe. Now, here, the universal set, the universe, are integers from 1 to 11. Listen carefully. A will be the set of all the numbers, and B be the set of prime numbers. Now your task is to draw a Venn diagram for this information. Okay, use your pen and the notebook. Please do this one. So you need to have a rectangle to represent a universal set. Inside, for this task, you should have two circles, A and B. And A and B, should they be overlapped? Some parts? If yes, you need to put those common elements in the overlapping part. So what is your answer? Have you got something similar to here? It's difficult for me to see your answer, but compare with here, the answer here. Have you done it correctly? Okay, so we have A and B. A is the odd numbers, 1, 3, 5, 7, 9, 11, and B are prime numbers, 2, 3, 5, 7, 11. These four are common elements from both sides, so we put them in this overlapping part. All the other even numbers except for 2, okay, they are in this universal set. That is how you draw a Venn diagram. Now let's have a look at what operations can be performed on sets. Here is the first one. Set unit. Set union. Sorry about this. Okay, this is our second one. Let's have a look at the first one first. So two sets may be drawn together to form a new set containing all of elements that are in one or the other or both of them. Okay, so when we write set union, we denote them like this: A union B. So A union B, the outcome, the result is a set. Remember in the first slide, when you write a set, we should have curly brackets. Inside, we have elements, and we use commas to separate those elements. So for this one, we have curly brackets. Inside, we have these 6 red-colored numbers, 2, 3, 4, 5, 6, 7. Okay, that is for A union B. Basically, A union B includes elements in set A and also elements in set B. Because for sides, we don't have repeats. So 3 and 6, you read only once. So 6 elements for this union. Now, next one. Set intersection. Two sets may be joined together to form a new set containing only the elements that were in both of them. Again, A and B. That is A intersection B. Okay, intersect with B. The output should be a side. Curly brackets inside. Inside there are 2 elements, 3 and 6, separated by comma. This is the second operation. Now, next one. Set subtraction or difference, sometimes we call it. So two sets may be joined together to form a new set containing only the elements that were in the first, but not the second. So we want to, here is our set A. Okay, we need to subtract those elements that are in both set A and also in set B, that is 3 and 6. So for set A, after do this subtraction, what we have, this one should be equal to a set. We have curly brackets. Inside, we have 2, 5. That is the result for subtraction. Now, the last one, last operation, complement. Have a look at the definition. The complement of a set A is the set of all elements that are in the universe but not in A. So have a look at here again, the same set A, all elements that are in universe but not in A. So we need excludes those elements in A, and then write it down. Here is the set complement of set A equal to curly brackets. Inside we have 1, 4, 7, and 8. We use commas to separate those elements. So you have already learned 4 operations on sets. Number 1, union. Number 2, intersection. Number 3, subtraction or difference. The last one, complement. Okay. More exercise for you now. Use your pen and notebook. Do these 4 questions, and then we discuss it together. So what is the first one? A union B. Write it down your answer first, and then I show you my answer in the OneNote whiteboard. So what is intersection of sets C and B? Next one, what is the complement of union of sets A and B? The last one, what is the set formed by subtracting intersection of sets B and C from set A? A little bit complicated here. Now, let's have a look at the answer here together. Have you done these 4 questions correctly? So A union B basically includes all elements in A and also all elements in B, but you don't do the repeat, okay? Only write B and C once. That is the first one. Second one, C, intersection between C and B. C is here, B is here, the overlapping part is here. So we have curly brackets, inside we have C and E. If we write side, there must be 3 parts, okay? We have curly brackets, we have elements names, and we have commas. Unless it is an empty side, we don't have, elements inside. Now for this one, how do you do this? Do A union B first, get here, and then do the complement to check which one in the universe side are not included in this set. So we have F and G here. The last one, again, do this in the round brackets first. That is B intersection C, B and C, that is this part. And then we do subtraction, subtract here from A. Only C is in A. Remove this part, the left is here. It's shown here. Okay, good. A little bit more about sets. Now power sets. Each set has a number of possible subsets. We talk about subsets, we talk about proper subsets. For example, for a set A, we have 3 elements, 1, 2, 3. The possible subsets are empty set. This one is based on the definition. And then 1, 2, 3, each element can be a subset of the original set. And then we can have different combination, 1, 2, 1, 3, 2, 3. Finally, the whole 1, 2, 3. This one is a subset of the original set itself, but it is not a proper subset of the original one because it is equal to the original one. All the others are proper subsets of the original one. The power set of a set S is the set containing all possible subsets. See, like what we have already listed here. Okay, and importantly, power set is a set. So we need to put every element here into a pair of curly brackets and use commas to separate them. So the whole thing here is the power set of A. Now, how do we calculate the cardinality of a power set? Here is a general equation. So we have this set. Calculate the cardinality of set A, and then the power set its own cardinality, basically it's 2 to the power of the cardinality of set A. So for this one, the cardinality of set A is 3. The power set here, we have 8 elements here. That is can be also calculated using here. That is 2 to the power of 3. It gives us 8. Okay. I didn't highlight the titles for this slide here because this is just to give you an idea what can we do with sets. We can use sets to do many things. For example, in databases. Okay. Maybe here it's easier to see. We can consider in databases we need a lot of tables. So here is one table for students who registered on one module, module 1, and here is a group of students and tutors registered on second module, and we can use set. Basically here we have 2 sets. We can use union 2 tables to produce a new table. So this is just one application by using sets. And another application, as you will see very soon, sets are used in probability. We use sets to describe outcome space and corresponding event. In Unit 6, you will learn that. Okay. Signatures. Remember when we talk about learning outcomes, I said the last one is you need to know how to write sets in comprehension. This is a preparation for writing in comprehension. So signatures. Look at here. What is here? This is signature. It tells us that the value named by this X is drawn from the universe of values U. Okay, this is called signature. Now, we talk about sets written in comprehension. Previously, when we write sets in curly brackets and then use commas to separate the names of elements. Those are called sets in extension. Okay, that is set in extension here. Now, we focus on set in comprehension because quite often when you read research papers, you see researchers use set written in comprehension. Now, look at this example. The curly brackets is similar to here, same to here, to denote this is a set. Inside the brackets, we have 2 sections. They are separated by a vertical bar here. To the left of this vertical bar, we give, what is this? This is we just talk about, this is called a signature. Signature tell us values here for X, they are drawn from natural numbers. To the right of this vertical bar, we state the condition that each element in the set must satisfy. So here it tells us in this set, we have values starting from 0 and ending at 49. They are natural numbers, right? This is in a much more concise way to write sets. Otherwise, you need, if you write it in extension, you have to write 50 numbers, right? This one looks much concise. Here, the conditions can be have more than one. See, the condition in the set comprehension is a true valued expression, true or false. So we can have more than one conditions. Here we have same signature. X is drawn from natural universe, natural numbers, and the X are greater than 10 and less than 50. So here, we are almost perfect. The only thing is here and. How can we make it more, looks more mathematical? So let's have a look at here. Using logic symbols. 3 symbols. If we want to say and, here is the symbol you should use. If we want to use or, here is a symbol. And this one is not. So just now we talk about, I don't like that and. We want to use a symbol to denote and. That is the proper way how to write. So in this one, signature to tell us X is drawn from natural numbers. And here, this X in this size must satisfy 2 conditions. One is X greater than 10. The other one is less than 50. Now, exercise for you today again. Use your pen and a notebook, write it down. You have been given 2 expressions, set expressions in comprehension. Please write it down, both sides in extension. So, what is your answer for the first one? What is your answer for the second one? Sorry, I simply cannot read the chart today. Not that easy, I don't know why. But, okay, is it here? Not this one, that is something different. Okay, let's have a look at the answers together. Have you done this one correctly? The first one. The first one says, okay, here is set in comprehension. And we have vertical bar. To the left of this vertical bar tell us as they are elements in this set, they are drawn from natural numbers. And to the right of this vertical bar shows the conditions. Conditions inside the round bracket says, okay, all elements greater than 10, but here it says not. So in total it says not greater than 10. Then what do we have? Not greater than 10 can equal to 10, right? So we have numbers from 0 to 10. They are positive integers here. 0 and from 1 to 3 positive integers. Next one. Similarly, as again, all elements are drawn from natural numbers. 2 conditions. One is less than 10. The other one is greater than 5. So if I draw here natural numbers in this number line, we have from 5, that is here, the condition greater than 5, we have values in this side. And then we have another one less than 10, we have 10 here. I use the whole here to denote this side, this side shouldn't include 5 and 10. So what are those numbers left? Satisfy both conditions and drawn from natural number. There are only 4 elements, 6, 7, 8, 9. Have you done them correctly? Okay, now before we carry on with this Cartesian product set, let's think about so far what have you learned in this session? We have learned the definition for a set, right? How to write a set in both extension and in comprehension. So think about it in your mind. You can draw a Venn diagram to describe relations among sets, right? You have learned 4 set operations: union, intersection, subtraction, complement. You have also learned power set and how to calculate cardinality of a power set. Okay, of course, you also learned some symbols like is a member, is not a member, subset, proper subset, and or not, logical symbols. Okay, now let's have a look at Cartesian product sets. What are they? So, looking at this map, how can we describe this church's location on this map? Each square here of this map can be an element of this site. You see here, map grid is the site. So here is a definition for this site, because we see curly brackets and we see commas. Inside each comma now is quite different from examples, those examples I showed you earlier. Now we have, round brackets. Each round brackets, we have a pair. Now have a look at the definition. We write S cross T to denote the Cartesian product of 2 sets. So this symbol is usually read as cross. It is very important for you to realize, okay, to know this. S cross T is not equivalent to T cross S. That is because here, inside of each pair, the elements, okay, those elements inside of each round bracket, they are all ordered pairs, followed, this order, that is S and T. So what I'm saying is, here is an example. We have 2 sets, A and B. A are alphabets A, B, C. B has 2 elements, 1 and 2. A cross B, we can write, see, A1, A2, B1, B2, C1, C2. So inside of each this pair, they are ordered. Follow which order? Follow here. Depends on which side cross which side. So the first will have, the first element comes from the first side. The second element comes from the second. When we have A cross B, you cannot have an element in this set, say, okay, in the round bracket, we have 1, comma A. That is not correct, because 1 comes from the second set. Okay, so inside here, each element in the round brackets they are ordered. So don't be confused with what we said earlier. There's no order in the sets. That means, okay, I can swap the first element with the second element. Here, each element is a pair of 2 smaller, elements here. It may be easier because it's maybe easier if I write it down here. If I say A, sorry. If I say A cross B, I can have A1, A2. This is correct. Okay, A we have A, B, C, and then B we have 1, 2, 3, for example. I can write it. I haven't, sorry, if I make it simpler, just this, just here, okay, make it simpler. So what I have is B2. This is correct. Now let me ask you, what about, is this correct? Is this correct? According to, on the very beginning we said there's no order in set. Okay, that is correct. That is correct. I can exchange or swap positions between, this is one element, this is another one, this is third one, this is fourth. I can put them in any position in the curly brackets. That is all right. However, if I write this, this is not correct, because what we want is A cross B. So the first element in each here, in each pair here, should comes from the first set. The second one should comes from here. Okay, so this here is okay, here is okay, but not this one. This one should be okay. So I hope I have already made it clear. Now, let's continue with this example. What do we have? Can you tell me? Or we do it together. We can have, this one is lamps cross lamp states. We can have red on or red off, green off, green on, and yellow off, yellow on. So 6 elements inside these curly brackets. Each element is a pair, including the first element comes from lamps, the second one comes from lamp states. Exercise. So can you tell me, is this correct or not? True or false? The first one. Oh. Sorry. That's good. I just want to see your answer here. So the first one, very good. It is false, okay? Because this one is not one of them. We have 312, but this is not right, okay? The order inside each element here, pairs, is important. Now, next one, the second one. Is it true or false? Excellent. The second one is true. Lovely, lovely, great. The third one, is this right? Lovely. This is correct, yes, or true. Okay, you say true or false. This one is correct. So order for each pair, I mean, each element here in curly bracket is all right. doesn't matter. You can put whatever, but inside each element is the pair. You see, the order should be the same. Okay, so that's great. Now, the second question, the second one. For the first one here, if we write it in, in cardinality, Cartesian products, what do we have? In extension. Okay. Can you see it now? So we should have, listen carefully, we should have 6 elements for the final result. We have inside, we have 1, 1, 1, 0, 10, 1, 10, 0, 100, 0, and 101. But how do you write them? You need to write them. Let me see if I have a. You need to write them neatly. Okay. So each of them, each pair are in round brackets. They are separated by a comma again. The next one is here. You see, they are different. One is this side, set A cross set B. The other one is set B cross set A. So they, okay, decide the order in each pair here. Okay, is it clear now for this one? I hope so far it is clear. And let's have a look at the Cartesian product. So far we have seen just the 2 sides, but you can have more than 2, 3, and even more. Like what we use, you see, databases, we talked about it earlier. In a complicated databases, it's usually, we can have many tables. So let's talk about relation. Why we have this Cartesian product? A relation from A to B is a subset of Cartesian product, A cross B. Any subset of A cross B can be considered as a relation. Okay, so this relation can be an empty set. Relation is a set, a subset of Cartesian product. It can be the entire set, can be empty set, can be anything in between. So before I give you an example, let's have a look at here. So binary relation. Okay, let me show this first. I think it is maybe easier. Can you see here? So I have earlier lamps and the lamp states, right? We have red off, red on, and we have green off, green on, yellow off, yellow on. This is my Cartesian product set. Lamps cross lamp states. Now relations. Any relation is a subset of the Cartesian products. So in other words, for example, here I can have relation 1. I have only red off, green on, yellow off. This is a subset of here. So this is a relation. I can have, of course, another subset, red on, green off, yellow off. This is another relation. What is binary relation? When we consider only 2 sides, one universe and another one. One universe includes my subset lamp, and the other one includes my another subset set that is lamp state. Have a look at this universe, the first one, lamp. We have, in lamps, we have red, green, yellow. In the whole universe, we may have all colors, pink, blue, all other colors. So the whole universe, we can call it source. Now here, lamp state. In our here, we have on and off. In the universe, I can add another one, broken. Lamp is broken, right? So the whole universe here is called target. But what we have already used here in our relation, this is just a subset of the whole universe here, is called range. For the source, the subset we used within this source is called domain. Those values are the first value in each pair. And range or target, those values are the second element, the second part in each paired, this ordered element. Okay, so simply remember here, relation is a set, is a subset of Cartesian product. And the source here, domain is a subset of source. Range is a subset of target. And domain, values in domain will be in the first in each pair here. Values in range will be the second. That is what I try to say in this slide. Example, here we have square in extension. So what does it mean? Giving a value, the square of the 0 is 0. Given domain value here is x, x equal to 1. So the square of 1 is equal to 1. Given 2, the square of 2 is 4. So this site, the name of called square. So square in extension, we list all elements here. Now domain of this square are natural values. Range of square listed here as a set in extension here. Okay, we can use size in Python. What I want to emphasize is that for next week's practical, as you can see from my screen here, okay, we have set to use set. What you need to do, you import a class Finite Set from SymPy. Here, I want to draw your attention because previous terms students made mistake. This one is capital F and the capital S. If you change it to little case, it won't work. It will report your error message. Now, in this here, in this cell, I actually created 3 sets, set 1, 2, 3. Set 1, finite set, we have none elements. Set 2, there's no elements here. This is an empty set. Set 3, we have 4 elements. So let's run it. Now, I can call for a method, is proper subset. So set 1, we have 4 elements. Set 2 is an empty set. Based on definition, what is your result? Set 2 is set 2 a proper subset of set 3. So let's run it. Think about your answer and then compare with here. If I run it, that is true. Empty set is a proper subset of set 3. Okay. Now, what about set 1 intersect with set 3? This is our set 1, set 3, intersect. You have your answer in your head now. So let's have a look. These are the set. When we write it down in your notebook, this is our set. Here, the reason we don't use curly brackets, that is because this is the Python function. Okay, so that is for this session. Let's have 5 minutes rest. Is it all right? 5 minutes. So we come back at 5 past, I think now it's 6 past 4. Okay, we start our second session. Thank you.
Recording stopped.
Hello, Mano. Are you there?
Yes, I am. Hi,
Oh,
how are you?
Hi, I'm fine. It just seems like one or two students cannot join this lecture. I don't know why. It seems like the Zoom link has some problem. I wonder whether it is possible for you to post the link again through discussion.
Link about what?
About this lecture.
Okay. Yes, I will
from
do this.
Zoom. Yeah, if you
Yes.
can copy so that. Yeah,
Yes, I will
okay.
do this.
Okay, thank you very much. And everyone at the same in time, let's start. Okay. Let me share my screen and then I make a recording. Thank you, Mano.
You're welcome. That's all right.
Recording in progress.
Okay, let's have a look at the outcome, learning outcomes for this session. So we will talk about the domain and the range of a function, how to graph a function, what are odd and even functions, how to find the inverse and composite of functions. We just talked about in the last session, okay, about relations. Relations are sets, subsets of a Cartesian product. Now, a very important distinction can be made among all relations. Any relation can be classified as one of these four: many to many, many to one, one to many, and one to one. Okay, so this is one to one. Every element in the domain can have a exact specific output in the range. Many to one. Okay, many is three elements in domain has the exact same mapping or image in the range. Many to one. One to many. One value in domain in this site has many different images in here, in the target. Many to many. One here can have different images in the target universe. And here, this one, the same target, if we trace back, you can find different value in the sources here. So we have many to many. Now, four relations, only two of them can be functions. That is many to one and one to one. The other two, one to many to many, they are relations. They are not functions. So have a look at here. Let X represents the elements of the domain, Y represents elements of the range, and F is the symbol for the function. So we can write F, you see here is a symbol for the function. Here, fx, that is the image of x with respect to the function in the range. We have an example. If to each number in this domain, there's a number. What is this? This is a function, okay, defined by here. Then the interval that is domain is called domain, and the interval that is output from this function in this range is range. How we write them? So domain here is the set of all possible x values which will make the function work and will output real y values. While range here is the resulting y values we get after substituting all the possible x values. Have a look at another exercise here. 4 images here, plots here. Which one is or are functions? Think about it. Based on what I said earlier, there are 4 types of relation: many to many, many to one, one to one, one to many. Only 2 of them are functions: many to one, one to one. So think about that and then make your judgment. Which one is a function? Okay, let's have a look at it together. You have your answers in your mind now. Let's have a look at it together. The first one, have you done it correctly? This one is a function. Many to one. Okay, we can have one here, we can have many to one. So this is a function. What about this? This is not a function because here in the domain for this one, we cannot find an image in the output here. So this one is not a function. When we consider whether it is a function or not function, you can see here every element in the domain should have an image in the range. However, it is different from here. In the range, it is all right if for one of them here, 2 of them, we cannot trace back in the domain. It is all right. It's still function. For function, we need to consider every element in the domain here. What about this? Have you done it correctly? Why this is not a function? Because this is a one to many. One to many is a relation, it's not a function. Now, 4 types of relation, only 2 of them can be functions, one to one and many to one. Now we can also classify our functions. The first one is injective function. Have a look at the definition here. So what are we emphasizing here is that in an injective function, every element in A is mapped to a different element of B. So I want to emphasize 2 keywords here. One is every element in A mapped to a different element of B. Have a look at the second one. Injective functions. Here, we would like to emphasize this time every value is not in A, but in B. Okay, in surjective function, every element in B, that is our, if you think about it, think about range here, is mapped to by at least one element of A. But every element you can find, trace back to the domain. So injective and surjective is every element considered are different. For the injective, every element in A. For surjective function, every element in B. Bijective functions. For those functions are both injective and surjective. They are bijective functions. Okay, to see whether you understand it correctly or not, here is another exercise. Which one of these is injective which one is surjective, which one is bijective, which one is just a function, but none of those injective, surjective, bijective. So, what is your answer? Okay, have a look at answer altogether. The first one is not a function. Why is that? Because here we have one to many. I said earlier, only one to one, many to one can be considered as functions. This one is one to many. This is not a function. And this one, okay, is just a general function. It is not injective because in injective function, every element, right? We consider the every, that's right, all right. But every element in A should have different values, maps in B. But here, these two get the same. So this is just a general function. This is not a surjective function because for surjective, we consider every element in B, but here, this one is not considered. So this is just a general function. This one is injective function because every element in A can be mapped to a different value in B. This one is surjective. Every element in B can be mapped back to A. Okay, can be the same, can be different. Here, this is a bijective. Okay, one to one. Have you done them correctly? How to graph a function? For a simple function, it's useful if we can visualize them. Okay, now how do we visualize them? Usually, you take some values uniformly taken from the mean and then calculate the corresponding y output value in the range and then plot, draw those dots and then connect them to get a graph of a function. This is an example. The interval or the domain is defined for x between -3 to 3. And the function is given by here. That is x to the power of 3. The interval or the domain is here. And when we calculate values for these domain values, we get, using this function, we get this interval is called range. We can plot, it looks like this. There are some properties about a function you need to understand. Let's have a look at the first one, bounded functions. Upper bound and lower bound. If there's a constant m such that this function's values equal or less than this m for all x in an interval, then m is called an upper bound of the function. Lower bound. If there's a constant m, little case m, such that all elements outputs of this function greater than or equal to this m for all x in an interval, then m is called a lower bound of the function. When we write the bound for a function, we normally write it down in this way. Okay, this is the bound. Can be, don't be confused with what we just talk about the cardinality. We also use vertical bars. That is for the sides. Yes, the number of elements in each side. But here is a bound. Now, look at this figure. Is this function bounded? It is, right? It is bounded. But the question now for you is, does it have a lower bound or upper bound or both? for the given interval, that is -5 to 5 for x value here, it is within this range, this function is bounded, and it has a lower bound that is 0 here. Okay, lower bound, this one, because all the values for this function are greater than or equal to 0, greater than 0 or equal to 0. So 0 is a lower bound. This function is also bounded at 25. Okay, so that is every element within this -5 to 5, this function's outputs are equal to or less than 25. So 25 is an upper bound in the interval that is between -5 to 5 for x. Why do we need to consider this bound? Here is the example. Some of you are learning the other module, that is machine learning and neural networks. So gradually you will learn activation function in neural networks. So here is a very interesting example. Let's talk about this one first. So here we have a function. A function is given by x plus 10. And x is, in the interval, belongs to interval -1 to 5. So given here, an upper bound is 15, the largest value x, x5 plus 10. That is, for this function within this range, every number, okay, is less than or equal to 15. So 15 is an upper bound. Okay, but it is not the only upper bound. We can have 20. 20 is greater than this function. So 20 can be another upper bound for this function. Okay, so this one is called the smallest upper bound. On the other hand, when we take the smallest value for x, that is -1, then added up here, we have the value for this function is 9. So 9 is a lower bound. All the outputs for this function, when we take values for x within this interval, okay, the function's value is greater than here. Of course, we can find much smaller value as lower bound. For example, 6. Every output within this interval for this function is greater than 6. So here, this 9 is called the greatest lower bound for this interval. Here, this is a very interesting function. It's called the sigmoid function. I think you will learn it very soon if you haven't in neural network and machine learning. Some of you, okay, register for that module. So why do we need to learn the bounded function? For this sigmoid function, as you can see, the output of this function is bounded within 0 and 1. It can be used to simulate probability values. That is the probability of an event happens or not happens. Okay, so probability is a value between 0 to 1. That's why researchers actually are looking for and still looking for some functions having nice properties. For example, like here, this function, the output values is always within 0 to 1 and can be used to simulate probability values. So the number one properties for function we talk about is bounds. Now, monotonic functions. Monotonic increasing. In an interval, if for any 2 points, x and y, x1 and x2, if we have x1 smaller than x2, the corresponding fx1 is less than or equal to fx2, then this function is called okay, monotonic increasing. What I mean is here, if we have x1, the corresponding value is fx1. And here we have x2, the corresponding value is fx2. x2 is greater than x1. fx2 is greater than fx1. So this one is increasing function, monotonic increasing. When we don't have this equal here, then it is called strictly increasing. On the other hand, if we have a function here, looks like this, we have x1, x2. The value of x2 is greater than x1, but on the other hand, the corresponding function value fx2 is less than fx1. Then this function is called monotonic decreasing. If we don't have this equation here, equal sign here, that means this function is called strictly decreasing. Okay, so we consider whether the function is increasing or decreasing. Now, odd and even functions. How do we judge whether a function is odd or even or neither of them? We use two ways. One is look at, if we have the plot for the graphs for a function, we can have a look at the graph. If it is odd function, then the graph here, you can see this function is symmetry about this origin. Okay, we call it origin symmetry. If it is an even function, then the graph is symmetrical around about this y-axis. That is one way. You can see this through graphs. The second way is to use here two equations to check whether your function, the function is odd or even or neither. One is here, when we substitute negative x value inside the function. If it is equal to the function itself, it is called even. The function is even. If it is equal to the negative value of the original function, then we call it odd. So two ways. One is observe it from graphs. One is using here. So here I give you two examples. Let's have a look at here together. The first example, that is, we have this function. To judge whether that is odd or even, we substitute negative x value inside this function. Okay, that is what we get. So compare this one with the negative value for the function here. That is what we have. Negative, the function is here inside here, and then what we have here is equal to what we just got here. So that is why if we get here, these two are equal to each other, then the function is odd. On the other hand, if for this function, for example, I substitute negative x value into this function, the function is defined as here x squared. So negative x squared is still x squared minus 35. So substitute negative x value into function. The function value is not changed. It's still equal to the function itself. Okay, this one satisfies here this equation. So that's why this function is even. Now, your time to do one more exercise for today's lecture. You use those two equations, substitute negative x value into each of these functions, and then tell me whether the first one is odd or even or neither, same to the second one. And let me try if I can see your answers through chat. Okay. You. Okay. Okay, I see some of you are really quick. Very good. Okay. The first one, both of them are odd. Okay, I see some answers. One said the first one is odd, the second one is neither. And another student said, okay, good. Another student said both are odd. Both are odd. I saw, yeah, first one. Okay. So shall we do it together, or let's have a look at my answer to here. This is my first one. This is my second one. Okay. The first one, this is the given function. Substitute negative value here inside this function. And then sort it out. That is what we get. Compare this one with negative function here, value here. We get things, they are equal. So we call it, this function is odd. So your answer, majority of you have already done it correctly. Now, that is the second one, you get different answers. This is the given function. I substitute negative x to this function. And that is the result here. Compare this one with the original function. They are not the same because here is positive, here is negative, here is negative, here is a positive. Also here are +1. They are not equal. Now compare this one with negative function values. Negative function values are given right here. Are they equal? The first term, they are the same. The second term, they are the same. But the last term, they are not equal. One is positive, one is negative. So this function here is not equal to the original one, is not equal to the negative one. This one is neither odd nor even. Well done. Okay, for those who have already done it correctly. For those, if you get the wrong answer, I'm sure there's some, maybe silly mistake in calculate this. So when you do the test or do your tutorial question in the tutorial handouts, so take extra care, be careful. Okay, well done. Now, inverse functions. We talk about so far properties. Increasing, decreasing, odd, even, and also what else have we talked about? Bound, upper bound and lower bound. Now one more thing before we talk about the composition. Here, inverse functions. Inverse functions, suppose we have a function, the relation between the domain and the range values, if it is 1-to-1, it's not many to one, just 1-to-1. Then a new function can be created by interchanging the domain and the range. Okay, and here we use this symbol to denote this is inverse function. Okay, this is not to the power of -1. Okay, this one is inverse function. And we consider only 1-to-1 relation. It is convenient to rename the domain variable as x and the range variable as y, even after we do this inverse. So what I mean is, let's maybe have a look at an example. It is easier together, you see. Here, this is a function. The aim is for you to know how to find the inverse of this function. So 3 steps. 3 steps. First, let this function, if it's not yet, okay, set it to equal to y. Then we have y equal to this function. This is first step. Second, make x the subject. So rather than have y equal to, we want to have x equal to. So what we do here, y plus 3 equal to 6x, and then x equal to here. Now, that is what I meant earlier. Replace y with x to obtain this inverse function. Because in convention, we would like to use x to denote domain and y to denote range. So that is how you write it. You see, we exchange, you see, replace y here to x. And then here, this x is just the inverse here. Now, can you do this question now for this one? Oh, oops, sorry. Again, follow 3 steps here. First step, let this function equal to y. Second step, make x the subject. And then the third step, replace y with x to obtain inverse function. Have a look at the answer together. So the first step, let this function equal to y. And then second step, make x the subject. Okay, so basically y minus 10, that is what we have. And then we have cubic root for this one. Now replace this y with x and then obtain the inverse function. That is the final result. Have you done it correctly? Okay. After we have already learned how to draw graph of a function and some properties of function, when you are giving a function, think about the bounds, the monotonic increasing, decreasing, and think about whether it is a one-to-one, whether you can find a inverse, whether it is odd and even. Those properties may be useful for your analysis. Now, let's have a look at some function examples. The first one in Unit 5, we will use it to develop a simple linear regression model. So here, this is a linear function. A linear function usually has this form. We consider only one input or only one variable here. And A0 is the intercept, a constant term. So let's consider several different cases. If A1 is equal to 0, all we have is y equal to A0. A1 equal to 0. All we have is y equal to A0. Because A0 is a constant, so what is the graph of the y? Then y is a horizontal line. Yes? So this is one case. Now let's think about what if A0 equal to 0. And then here we have some non-zero value. Then the line will pass through the origin. So in this graph, if here A0 equal to 0, y equal to A1x, suppose A1 is not equal to 0, then we should have a line passing here the origin, either in this direction or in this direction. The third case, let's consider. If A0 is not equal to 0, and here A1 also is not equal to 0, then we have two cases. They were drawn here. One is, for example, here is A0, okay, a positive value here, constant. And A1 is equal to 2 first. Then we have this red line. the slope is positive. On the other hand, here, the slope here, A1 is negative. That is what we have. Okay. So slope here denotes the direction of the line. This is a linear function. In Unit 5, we will come back to use linear function to develop linear regression model. Next one, we'll have a look at a polynomial function. These are functions built out of non-negative integer powers of x. For example, here, x to the power of 2 within this interval -5 to 5. You start with the building blocks like x to the power of 0, x to the power of 1, x to the power of 2, and so on. And you are allowed to multiply these basic functions by numbers and add a finite number of them together. For example, there's a function fx equal to f multiplied by x to the power of 3 plus 3 multiplied by x to the power of 2 minus 10. This is just an example, right? That is a polynomial function. Now, this function is not injective. Remember, for injective, every element in the domain should have a different value in the range. But here, in this one, here, two elements in the domain may have the same, you have the same value in the range. So this one is not injective. That means we just talk about inverse function. Inverse function only works for relationship, say 1 to 1. So this one cannot have a inverse function. So in other words, say for example, if we have a, say, for example, and this x is not saying greater than 0 or less than 0, okay? What we have is x equal to r, okay? The whole real line here is my x. Then here, if I want to do, see, x equal to, that is what we get. Remember, for the function we said, we need 1 to 1 or many to 1. Here, for the same value, we have two images. So that is what we meant here. That is not a function when we consider the square root. If we don't limit the interval for x, if we actually set remain x only for positive, then that is okay. And not, you see, in this case, we have both positive 3 and negative 3. Then that is not a function. Okay, so most important point you should remember is when we talk about the inverse function, the inverse function is when we consider 1 to 1. Only for 1 to 1 we can find inverse function. So this is polynomial. Polynomial function will be also mentioned when we talk about the linear algebra, linear regression model. Exponential function. Here are two figures. I'm sorry, this looks a bit small here. Make it a little bigger. All I want to say here is that we have exponential function looks like this. One here is 2 to the power of x. So a here in these two plots, a equal to 2. And the x, 1 is to the power of x, 1 is to the 2 to the power of negative x. So as you can see, the graph, this graph here is just the reflection of this graph in y-axis. If we put them together, this one is a reflection of this figure in y-axis. Okay, so exponential function is injective. It is also surjective if we consider the codomain to be the set of positive real numbers. What is codomain? Codomain is another name for the same, for the target. The inverse function of it is log function. Exponential functions are very important in data science. When you learn random variables in Unit 6, you will see a Gaussian distribution of a random variable is in fact a member of exponential function family. It's from that family. So that is why exponential function, it is very important in machine learning data science. Another thing I want to say is here, both sides here, there's a horizontal asymptote at y equal to 0. That means, okay, the curve doesn't touch x-axis, no matter what looks like on your graph. Looks like, oh, this is equal to 0. Actually, it's not. That is something I want to emphasize. Okay, logarithm function. The log function is another very important function in calculus and also in machine learning. Quite often, you will see a cost function or an error function is defined in a log likelihood format. Please not worry, okay, if you don't know what the cost function or error function is now, because you will see examples in Units 4 and Unit 5. But this is, we talk about inverse for the earlier one, the exponential function, exponential graph, and this is a log graph. This is the inverse. Finally, trig functions. Trig functions, I say, all the functions I show you here are very widely used in machine learning. These are useful for signal processing. So all signals in real life, okay, in real world application, every signal actually can be decomposed into all different this wave, sine wave or cosine wave, but with different amplitude, different phase value. So here, this one is also important to do calculus. You really need to know this, because for some times you may use these trig identities to solve certain type of integrals. In Unit 4, we will talk about integrals, but for complicated integrals, which we won't cover in this module, you will see, if you are interested in to see, okay, they actually have to borrow some identity functions from trig to solve integral problems. Okay, we have gone through some important functions which are widely used in machine learning and data science. Now, let's have a look at the last very important topic today we need to cover. Composition of functions. So far we talk about relations, 4 types of relation, right? Only 2 of them can be considered as functions, 1-to-1, many-to-1. And we talk about functions, how to we draw plot functions for simple functions, and the properties. Even for the complicated functions, you need to consider bounds for function and odd, even, and increasing, decreasing, and odd, even, right? Those kind of things. And we show you some important function figures. You learned how to do inverse, 3 steps. How to find the inverse function for a one-to-one function. Now, today, this is the last one, composition of functions. Let f and g be functions. The notations here raise f composite g. So first, we apply function here, g to x, the input. If we get an input, okay, it will be applied to the rightmost function first. And then the output of this g function will be the input for f. So have a look at here. We have 2 functions, f and g. F compose g. That means the output of g function will be the input of f. So the output of gx is x squared, x to the power of square. Now use it as input of this function. That is what we get. That is what we get. Exercise. So what is your answer for this one? What is your answer for this one? So always apply the input to the rightmost function first. The output of this part is the input of the leftmost here, because we only consider 2 functions here. So what is your solution? Have a look at the solution together. We have this function, we have here, and we want to do g composite f. So input x to f first, that is our output for f function, that is here. This one will be, is the output of this function, becomes the input of g function. So that is our final result. If we expand here, that is what we get. Okay. Finally, here. So far, we considered only one variable for functions. Now, in machine learning and data science, it is too common in real life problem, okay? Majority of them will have more than 2 variables, okay? The domain of a function of 2 or more variables is a set of n tuples of numbers. The range is one-dimensional, an interval of numbers. What does it mean here? Have a look at the example, this one. We have 2 variables, x and y. The output here is one-dimension value. So how do we write the main value for this part? What is this? This is we have already learned in the first session today. That is set. Yes. So this is a vertical bar. To the left of it, here we define. Do you remember the name for this? Signature. So it tells us x and y both are drawn from real values. To the right side of this bar, it tells us the conditions. X basically is everything we can take from R. and y must equal to or greater than 0. On the other hand, that means, okay, what if we draw it? That is, the shaded part are values, pair values we can take for this function. Everything along x real values line and y must be greater than or equal to 0. That is this part. Okay, before we finish for today's session, I just want to show a little bit more in Python code in Jupyter Notebook. For example, in your practical 1 and 2, you have already seen some functions defined or built-in function in NumPy. Say, for example, np.sine, np.cosine. Those are built-in function, comes from NumPy classes or package. So there are two ways you can define your own function. For simpler one, we call it lambda function. Lambda function. So in this function, the aim for me is to define a sigmoid function. Remember, sigmoid function, that was here, I showed you earlier. I think, sorry, I didn't remember which slide is that. Bounded, I remember. This one. This is sigmoid. Okay, have a look at the shape of here. That is 1 over 1 plus this value to the power of negative x. Or it can be written like this. The output of x, of y, this function is bounded between 0 to 1. Now, I use lambda. This is a keyword. Variable is x. I use colon to separate my variable from my expression here. This expression is sigmoid function. Remember, 1 over, in the denominator is 1 plus that e to the power of negative x. That is a function. How you can define function? Simple function you can define to use this keyword lambda. Now, I assign some values for x. X values comes from an interval between negative 20 to 20. And we have, I calculate, actually the Python calculate function value and then assign this function value to y. How I call this function? I call it, just in Python Jupyter Notebook, call it like this way. F, what is f? F is a defined function, lambda function here. I can call it and then here input x value that is claimed here. Now I got x and y. I can plot them using, you see, a plot function. I actually claimed here. Okay. MATLAB plot equivalent to matrix or MATLAB plot, okay, from that library. Now I plot this and then I show, let me show it, run it. Let me run it. I can show you the whole function. This is sigmoid function. You will do this exercise in your practical session again. Now, two ways to define your own function. We talk about lambda function here. There's another way that is a common way and widely used for even more complicated function. You use the keyword define. Here is function's name. You can give any name here. My first function, or you can call it a sigmoid function. It is your decision, but usually we use a meaningful name for this function. Similarly, again, this x is the argument input for this function, and then y we have here. That is we define similarly to that lambda function. Now we return function's value using keyword return and then y. don't forget you need to have a colon here when you define a function at the end of this DEF line. And then you can call for, similarly, in another cell, you can call for, you see, this function. This is function's name, like here. I leave it for you to practice in your next week's practical session. This is a part of the task, I think task 9 for you in the practical session. So that is for today. Thank you very much. And I will see you in on Friday's lecture. Before that, I have a drop-in session on Friday as well. Okay, thank you. Goodbye.